So I want to start taking a look at one of the things that we can use the dot product for, and that's to help us calculate the angle between two non-zero vectors in n space. Very important that we're working with non-zero vectors, because remember, the zero vector doesn't have a unique direction associated with it. But if I have two non-zero vectors, let's say I've got v and w, and you might say, well, wait a minute, there's no angle between them. Well, that's because I've drawn them in translated position so that they're not meeting anywhere to form an angle. But I could certainly translate w so that I could draw it so that the two vectors had their tails together. When I put the tails of two non-zero vectors together, they're going to form some angle. Now, by definition, the angle theta between the two vectors is going to be between 0 and pi. So it's going to be somewhere in the interval from 0 to pi. So when I've got these two vectors here, it's not this angle here, that would be too big, it's this angle here. And it's always considered a positive angle. So I'm not considering what direction I'm having to rotate in. That kind of makes sense because we're going to be using this in 3 space too, where the notion of clockwise and counterclockwise doesn't make a whole lot of sense. Just to illustrate that, I'm going to move my arm around. Does it look to you like I'm going clockwise or counterclockwise? It should look to you like I'm going clockwise. But I'm going to now turn around, and I'm not changing the direction that I'm rotating things. Oh my goodness, now it looks like we're going counterclockwise. So your perspective, where you're standing, depends on whether things are going to be described as clockwise or counterclockwise in 3 space. So we always simply define the angle between two non-zero vectors to be a positive angle between 0 and pi. And if I'm in 3 space, if I have a vector here and a vector here, just like in 2 space, I can translate them so that they've got their tails at the same place. Now, these two vectors, even though we're in 3 space, they lie in a plane. And it's in that plane, I would just twist that plane until it aligned with the whiteboard here. It's in that plane that we would measure the angle between them. Now, it turns out we've got a theorem, Theorem 3. If A and B are non-zero vectors in Vn, and theta is the angle between them. So, no period there. If that's the case, so if I have two non-zero vectors, either in 2 space or 3 space, I define theta to be the angle between them. A dotted with B will be the product of 3 things: the magnitude of A, the magnitude of B, and cosine of that angle. So this is why I was saying earlier that there isn't really a satisfying definition for what is the dot product, because it isn't any one thing. I understand geometrically what this means. That's the length of A. That's the length of B. That's cosine of the angle between them. I understand each of those 3 things, but the dot product is all 3 of those things multiplied together. So the dot product is going to be very useful in helping us to calculate the angle between two non-zero vectors, but by itself it isn't that angle. It isn't a trig function of that angle. It's the result of taking cosine of that angle and multiplying it by the 2 magnitudes. Okay, so we've got that. Now, of course, this can be rearranged, and I believe your book calls it Corollary 6 when they rearrange it to say that cosine of theta is then A dotted with B divided by the magnitude of A times the magnitude of B. I know that it's okay to divide by this because we stated that A and B were non-zero vectors. If A and B, if either one of them was the 0 vector, theta wouldn't be defined. This entire equation doesn't make sense. If they're both non-zero, then their magnitudes are non-zero, so it's totally fine to have that in the denominator. Okay. So this is just rearranging the formula that your book calls this corollary 6. A corollary is just another theorem that's sort of related to another theorem. Okay. Some textbooks would actually just state this as one theorem, and it's just a rearrangement of things. Notice we can then actually solve all the way for theta. Now, in general, if I just know that cosine of theta is equal to some number, that does not tell me by itself that theta is going to be inverse cosine of that number. Because if this number happens to be 1/2, there are infinitely many angles whose cosine is 1/2. However, by definition, the angle between two vectors is between 0 and pi. And that happens to be exactly the range of inverse cosine. So theta is arc cosine of A dotted with B over the magnitude of A times the magnitude of B. In order to do that, I needed to recall that theta had to be between 0 and pi. And let's just recall, theta is in this interval, and that exact same interval is the range of arc cosine. Okay, excellent. Now, I've stated this, we're going to actually go about proving it. Okay. Now, as we prove that, I'm actually going to break this up into 3 different cases. So case 1 will be if theta is equal to 0. So that's going to be when I have 2 vectors that are pointing in exactly the same direction, so that the angle between them is 0. Here, both of these vectors are pointing to the left. They're making an angle of 0. Now, if that's the case, my 2 vectors point in exactly the same direction, so I would say that A would just be some multiple of B, and it would actually be a positive multiple. Because if I take a positive scalar and I multiply my vectors to get my vector by a positive scalar, it does not change the direction. Okay. Case 2 is going to be the other extreme if theta is equal to pi. Okay. By the way, I haven't started a formal proof yet. I'm just sort of outlining what I'm going to do. Once I'm ready to do a formal proof, I'm going to need to identify my objects. Here I'm just outlining what I'm planning to do. Okay, so if theta is equal to pi, that's going to be a situation where the angle between my vectors is pi, so that they're pointing in exact opposite directions. So again, that's going to mean that A is a multiple of B, but in this case it would be a negative multiple, because if I multiply a vector by a negative number, it reverses the direction. And then case 3 will be if theta is strictly between 0 and pi. Now, the reason I'm going to need to have these 3 cases is that these 2 cases have A being parallel to B. We discussed parallel briefly. I don't think we've formally defined it. We say that 2 vectors are parallel if the lines determined by them would be parallel. That means they point in either the same or the opposite direction, so the angle between them is either 0 or pi. Basically, it amounts to 2 non-zero vectors are parallel if one is a multiple of the other. And if it's a positive multiple, they're going to have the same direction. If it's a negative multiple, they'll have opposite directions. Okay. Here, if they're not parallel, I can form a triangle. With A and B as 2 of the sides. And when we do that, we'll be able to use the law of cosines, which describes a relationship between, oh, the lengths of some sides and the cosine of an angle in our right triangle. But if they're parallel to each other, if the angle between them is 0 or pi, I'm not going to be able to form a triangle. So I won't be able to prove these cases the same way I can prove this case. All right, so that's sort of an outline of our plan. In the next video, we'll try and get through, I think we should probably be able to get through cases 1 and 2 in the next video, and then case 3 is the longest one to prove, most interesting one to prove, I think, and we'll do that in the following video.